In this lecture, we'll begin our look at coastal geomorphology and all of the unique sets of processes and landforms that are encountered when you're looking at the interaction between, in this case, wave action and a landform in a coastal region. It is important to remember that when we're looking at the interaction or the interplay between energy and matter in an environment such as a coastal landscape, we are really looking at, in this case, the energies that are associated with climatic environment. In this case, energy is fed into coastal geomorphic systems primarily by the work of ocean waves. Again, these waves generally will travel pretty significant distances with regard to their hemispheric patterns. And then we will see, as I said before, the local climatic conditions interacting with these environments. They're not as important as ocean currents, but they do contribute to the overall landform genesis and change with regard to coastal environments. As your author points out, a shoreline is a line of demarcation between land and water. Now, this line will fluctuate from season to season. It will fluctuate from geographic location to geographic location. And of course, it will also be significantly impacted by the actions of waves and patterns of tides. The shore zone, which becomes extremely important in our area of study, is simply the shore. It's the zone affected by wave action, and that's what we'll be taking a look at in this lecture today. To understand the geomorphology, the geometry that is associated with, in this case, waves, the movement, the oscillation of water particles, it's important that we as geomorphologists take a closer look at the length, the height or the amplitude, the velocity, and the period that is associated with a wave action. Let me set for you some of the definitions that are important to understanding what you're looking at here in this diagram and, of course, what I'm describing to you. A wavelength in this case, generally it's a aspect of data that is being labeled by L. This is the distance between waves. So when you take a look at where, for example, in this diagram, the wave crests are developing, these higher portions of a passing linear wave, where these develop, we identify them, and then we measure to the next wave crest, and this gives us an idea of the wave length, so it's a measure of distance. Period in this case is a measure of time, generally represented by T, capital T, time being measured in this case between passing waves. So the time that a wavelength develops, the time that we see a crest moving past a data point is going to give us a sense of period. Height or wave height, usually a lowercase h in a lot of the equations. This is the height from crest to trough. Really what we're looking at here is amplitude, as I mentioned before. So when you think about where a wave crest forms and where the trough forms as you are collecting your data, this will give you the difference between these two locations, will give you a sense of the wave height. And then generally, another important variable that is being considered is water depth. And you'll see how this plays out in the coming slides. Generally represented in most equations by a lowercase d. Water depth in this case is the average water depth that will be a factor of a wave action, or it will be connected in some way, shape, or form to the oscillation of water particles. Now, another variable that becomes very important in how we study the movement of water particles in a marine or freshwater environment is also velocity. Velocity in this case relates to the movement of points of greatest amplitude. So when you're measuring velocity, you can measure it from a variety of locations within a wave environment, but generally the velocity that becomes most important for being able to predict wave patterns and tidal movement will be the velocity that is generally recorded over long periods of time in the wave height environment, where we have that crest developing in a wave swell. Periods, as I said before, are a factor of this. They are defined as that interval of time that exists between these wave peaks. So what can we take from this? Well, variations in these measurements will relate to the mechanisms that drive wave actions in most local environments. And in studies throughout, in this case, southern and southeastern Wisconsin, including studies on our campus, we take a look at freshwater inland lake wave actions and how those impact, in this case, not only the beach environments and the shore line of our lakes, but we also take a look at how that impacts, in this case, plants and animals in the region. When we are looking at the Great Lakes or Lake Michigan, for example, and studying wave swells over long periods of time, we're really looking at wave action in a cool, humid climate type. The most important natural feature that contributes to wave action, and especially the energy that is associated with it, is wind. And this is why air velocity and the concept of fetch, or the geographic space that wind moves across as it is generating the energy required for wave actions and currents, developing currents. This is something that is also recorded. Fetch in a shoreline study, for example, will be the surface area of the lake. So if we're to take a look at a measure of fetch as it relates to Lake Michigan, we would take a look at the wind direction, of course, and we'll see this in a few slides from now. And then we would also, in a sense, take a look at how much space that wind is moving across as it is moving toward an area, a project area that we are taking a closer look at. And again, fetch and wind speed become extremely important when we're talking about the energy that is an input into the wave system. Wave morphometry is something that becomes important when we're trying to construct models for wave actions. In your readings, you'll see diagrams of waves. You'll take a look at oscillations within those waves, and a lot of what we're looking at here is factoring into that. Wave height, as I said before, is really, really important on a global scale. Geomorphologists will make estimates of global wave heights, and they will use some pretty basic formulas to do that. The first formula that we have here is where fetch is known. Generally, a geomorphologist will take the square root of that distance measurement and multiply it by a factor of 0.36, and this gives you a baseline understanding of the wave heights that would be common to a swell environment. In cases where wave velocity is known, generally a geomorphologist will square the velocity measure within that crest environment, or within at least one oscillation within a wave length, and then multiply that by a factor of 0.031, and that will give geomorphologists an average or baseline wave height measurement for a region. So there are a variety of wave types, and we'll take a closer look at two of these, but I'll describe three of them. Again, wind being the driving force, or the greatest disturbing force when it comes to the creation of waves. Waves, as you will read about, are also generated by earthquakes, volcanic eruptions, landslides, plate tectonics, and then of course we have tides, which are produced by gravitational kinds of interactions. In this case, it takes us all the way back to the interaction of the Earth, the Sun, and of course the Moon as well. The most common category, or the most numerous wave type, is a wind wave. Generally, in a wind wave, we will have speeds of globally 10 to 75 miles per hour. Periods, in this case, will be somewhere between 5 and 30 seconds. And then we'll also see, in this case, wave heights, really broadly ranging. We'll see small ripples on one end of that spectrum, and then we'll see things as much as 60 feet on average for marine environments, these wind wave environments as well. Tsunamis are things that are generally produced by either plate tectonics or something related to that. They are extreme. They cause significant loss of life, and of course, we see pretty significant measurements with regard to some of the variables we look at. Wave height can reach as much as 300 feet. Speeds, of course, the velocity of water particles can range as much, or can range up to, in this case, as much as 500 miles per hour. Periods, again, are generally measured in minutes, and we see wavelengths being regional. So we maybe will have wavelengths in a tsunami environment where we have, literally well over 100 kilometers of linear space being expressed in that wave. And then, as I said just a moment ago, we have these gravitational interactions which result in tides. Tides will generally be groups of waves that fit into a kind of a gravity category, and this is where we see heights generally up to and exceeding 50 feet, and we see periods of time associated with wave action that can take entire days or half days. So we can see ranges of anywhere from 12 hours to over 24 hours. Within the wind wave category, swell waves are the ones that generally will receive the most attention by, in this case, geomorphologists. Why is this the case? Well, they are much more regional in nature, and they are tied very strongly to ecological patterns. And of course, that runs a very wide range of data sets and data resources. But generally, they will be receiving the kind of most attention because they'll cover long periods of time across the Cenozoic period. The other advantage of looking at swell wave environments is that you will have very little variation in terms of wave periods, and you will see, at least on an annual or even daily cycle, you will see regular and very common kinds of wave environments. Breakers and how they develop and surf, these become extremely important in understanding the shoreline environment and the interaction between wave swells, wave actions, and a shoreline landscape. In deep depth environments, less than about 1/2 the wavelength, we see waves that begin to interact with sloping environments. And that's what you see here at the kind of base of the image. Above that, we have more of a sea wave environment. Generally, what we see is that oscillation patterns become very distorted. Things like shoaling or shallowing transformations will begin to take place. And so this really changes, in a sense, how the water particles are moving, and ultimately it will have the greatest impact on how these shoreline environments will change over time, how they'll develop and then, of course, change over time. In both diagrams, orbital velocity is something that is important to understand. It tells us something about how the wind and the wave is interacting with one another. It also tells us something about how the water particles are behaving, no matter what their depth is, and then how these water particles interact with a local terrestrial landscape. If you look at the base of the slide, you see a very important equation, the orbital velocity equation. Orbital velocity in this case is represented by the lowercase u. This is again the orbital velocity of a water particle. in a surface wave, a wave that is developing above the wave base. And then it basically is a function of pi, and the difference in this case, we divide the orbital diameter, or the wave height, by t, or the wave period, as I described before. So as you take those two measurements, you divide the height by the time, you multiply that by pi, and that gives you a baseline for the orbital velocity in your research environment, or within your project area, or along your research transect. And this is a really helpful piece of data because it gives us a sense of how water is moving over time. So we can take a look at the orbital velocity of a wave environment in close to the shore, or deeper in a kind of a sea wave environment, and we can really get a sense of how the local climate is impacting the behavior of waves rather, and how water depth is also a factor of what we look at. This becomes important because at depths in which we see waves beginning to stir or disturb bottom sediments, this is something that we can factor in as we look at how waves will move a beach environment or actively erode a bluff environment. The stirring of bottom sediments is often determined by the wave height, the wave length, the wave period, and of course the grain size of what the waves are interacting with. Ultimately the load, the physical load that can be caught up in these patterns of oscillation. Although very long period swell waves may stir water and bottom sediment to great depths rather, the rapid decay of the orbital velocity within or with depth ensures that ordinary waves will not significantly transport the eroded bottom sediment of a deep or an area of water depth that is greater than about 10 meters. So again, how deep that environment is and how these patterns of oscillation are interacting with bottom sediments become very important for understanding the idea of landscape change over time. This depth is called the wave base or the surf base. It is a convenient reference level, although we should keep in mind that the work of waves does not abruptly cease at a certain depth, but we should know it. So once we reach the deepest levels within a body of water, we really begin to see a change in the energy and the energy material or energy particle interaction. We also see a pretty significant change in terms of the movement of waves. And these oscillatory wave patterns are very important to kind of conceptualize as you're looking at how particles might be moved or how toxins might be moved through a surf environment. Ironically, when we're in deeper levels, when we get close to that wave base, there's very little actual forward movement of wave or water particles in this case. Water particles are recognized again to be moving in that kind of cyclical fashion. The cycles will be tighter, but much slower, and almost to the point of appearing to be in a very static kind of an expression. This limited motion will decrease even further as you go to greater and greater depth. So as you go even below the base wave environment, water can almost be at a standstill. So it's a really dynamic system when you start looking at how waves behave as they relate to, or at least how these oscillation patterns are manifested in relation to overall depth. This aspect is important when comparing the movement of water and water particles in a variety of bodies of water. The Wave base, for example, in a small body of water is recognized at a much deeper level than it would be in the middle of the Atlantic or Pacific. So when you're out in these kind of larger geographic spaces, we'll see wave base expressions slightly more shallow. So it's again it will give us an additional factor or geographic variable to consider. Are we dealing with a large water environment, or are we dealing with a smaller, more circumscribed kind of water environment? Another consideration that we have to make relates to extreme situations, in this case, storm activities, and how they impact oscillatory waves and wave environments. So waves generated by storms will have much higher measures in all wave categories, especially those associated with this oscillation that occurs within a developing wave crest. For example, in Lake Michigan, freshwater environment, if a wave period is close to 5 seconds or more, estimates of oscillation within the developing wave environments along the shores will express wave lengths of as much as 39 to 40 or more meters. And we will see average velocities increase. We'll see average velocities expressed at or around 0.7 to 0.8 meters per second. So it's a real phenomenon when you take a look at how storm waves will accelerate many of the things that we see on a daily, weekly, or annual cycle within an ecosystem, within a landscape. During recent storms, periods of 10 seconds were recorded with wavelengths of over 170 meters and velocities of 1.56 meters per second. So we've seen some pretty extreme weather patterns over the past few years, especially along, in this case, the western and southwestern edge of Lake Michigan. Here's an overview of the Shoreline Lab that is part of the curriculum of one of our courses, in this case, geomorphology. It is giving you a overhead view of, in this case, Bradford Beach, with a GPS coordinate and an elevation in the upper portion of the image. As you can see, Lake Michigan becomes very deep very rapidly as you move about 20 meters off the shoreline in this area. You start to rapidly decrease in elevation, and there is a point about 10 meters further out from that where we start to approach, in this case, sea level, and a portion of the lake itself will actually be below sea level. So it's a very deep lake environment, and it's one that, because of its significant depth, is of pretty significant interest to geomorphologists who are looking at waves and wave action, and how waves and wave action in a freshwater environment significantly shape or impact the coastline of this shore, of the shoreline. So it's something that continues to be of a pretty important study, and it's important to understand how, what the impacts ultimately are of eutrophication in this area. Generally, when we are studying a shoreline environment, such as the Bradford Beach area, we will develop research transects that will move, in this case, according to compass measurements. We will go due east-west or north-south from a shoreline environment, and along those research transects, generally spaced out between 5 and 10 meters, we will take recordings of everything that I've introduced to you in this lecture. We'll take a look at wave height. We will take a look ultimately at where troughs develop. We'll take a look at wave lengths, and we will record wave periods. Beyond this, we will also consider the lay of the land. So we'll get a sense of the shape and the angles associated with the shoreline. We'll also attempt to understand something, at least on an annual cycle, about the angle of the current in this area. So at what angle is the current flowing toward, in this case, a beach or beach zone, and then as that current interacts with that environment and is refracted out back into the deeper water, is it moving, at what speed is it moving, and what angle is it moving to the south and southwest? As we start to collect a lot of the data that is important to the work of wave morphometry, the amplitude of waves, as I said before, their vertical height and magnitude, and then the different kinds of wave types and breakers that we see developing in the surf zone. So these are also important to consider as we look at how a current will ultimately be impacting, in this case, a beach environment or a beach zone along the edge of a freshwater lake. Of course, fetch is also something that's important, and this will vary by time of year. So we'll take a look at wind direction and wind speed. We'll also, of course, take into consideration the geographic space over which the wind is moving and how that may be impacting the types of waves that are being recorded along those research transects, of course, close to the shoreline versus further out into the deeper water. And then also the amount of sediment that may be disturbed and may be gathered up into a wave environment and moved, in this case, to the south and southwest. When we take all of this into consideration and start to create a morphometry model for a wave environment and for a shoreline, we can really get a sense of how that shoreline will change over an annual cycle, but also over decades, if not centuries. And this is something that becomes really important to, especially an urban environment where you have city planners, in a sense, developing this landscape in such a way as to allow people to enjoy the Great Lakes for all that they have to offer, and then also providing information to county and city services who have to maintain the beach zone and maintain, in this case, beach in this area, because by nature and by how the waves develop in this area, really this beach is nearly completely artificial. It really, if you look to just to the top of the screen in this image, or just below the Bradford Beach environment, this is an area that is a little more natural in terms of what we would expect to see, given the shape of the lake, the size of the lake, and the cool, humid climate type that it is a part of. Let's take a closer look at how waves interact with landscapes as we start to see a more shallow water environment develop. So as we start to see, in this case, that base waves start to interact with landforms. So breaking waves occur in a continuum of types. However, it is the gradient of the intertidal region and the beach environment that seems to predict their type of break. This is why we have to record beach slope in our studies of wave morphometry in an intertidal environment. So there's really three major categories of breakers that we see, not only in a freshwater environment like Lake Michigan, but across the globe. The first one is a type of breaker called a spilling breaker. This is where water from the breaking wave moves down and across the face of the breaking swell. So as we start to get the disruption in the breaking swell, we start to get a slight crest forming. It's not as distinct as what we see with plunging breakers. We do see water, in this case, exceeding the crest environment and running down refracting back down the face of the developing spilling breaker. A second category is the plunging breaker type. This is where the crest curls over as we have even a higher kind of energy expression in that oscillation. It curls over the top and crashes down over the advancing wavelength, so it actually exceeds the trough and wave crest environment. It plunges back down over onto the next wavelength that's developing underneath it. And this is, the kind of thing that a surfer would be looking for. It creates that kind of barrel-like expression in its more extreme expressions. And then the last type, which is something that we see along developing coral reef environments, these are surging breakers. This is where breaking may not occur at all. We see this where water interacts with pretty extreme gradients or some sort of immediate change. So if you even have a seawall, you'll have these surging breaks that occur where it's just slamming into the seawall with pretty extreme force. We also see surging breakers along solution platform environments in those intertidal zones. And water and water particles will move pretty laterally, pretty extreme laterally as a result, generally parallel to the face of the steep gradient that's preventing them from having a more natural break, either in a plunging or spilling type. The last thing we'll take a look at are tides. Tides, again, take into consideration everything that we've looked at up to this point, but they take it to its greatest time scale. And even though they are organized on a seasonal or even daily pattern, they are, in a sense, much more attuned to the ecology of the planet and global patterns of climate change. Now, tides are also unique because generally the energy that is associated with a tidal environment has a lot to do with the relationship that the Earth has to the sun, and especially the relationship that the Earth has to the moon. So the moon and the sun and their ability to affect not only the rotation of the planet, but also the movement of water particles on the surface of the planet are things that are really bound up in the concept of an ocean tide. Let's take a closer look at three major types. So the first I have listed here for you are spring tides. These are periods of great shoreline intrusion and a general rise in water levels. There is a seasonality in this. So in Lake Michigan, this seasonality will have more to do with the meltwater and rainfall associated with the transition between winter and spring. And so you'll see an increase in warm air and wind speed from the south and the east as spring occurs. And this will greatly change the distribution of water within this lake environment, whether you are on the east side or the west side of this of the Lake Michigan lobe, or the Great Lake, Lake Michigan. And then a second group we have here, these mixed tides. The Pacific Ocean environment experiences generally a mixed tidal expression. This is where you have highs and lows in water levels that will be experienced within 24-hour periods. The last category are diurnal tidal expressions. This is where, again, we see or they are common rather, to a coastal Arctic environment where there is a single high and low expression that occurs daily. So if you've traveled, for example, through cooler portions of the northern hemisphere, let's say Alaska, you see more of these diurnal kinds of tidal expressions than you would along the kind of southern coastline of California. So diurnal tides are things that we're seeing more in these kind of Arctic or polar regions, or as you start to get into latitudes that will approach the Arctic Circle.